Alright, in this video we're going to start angular momentum. And angular momentum is not something that's just very easy to see, but we're going to start with something we kind of need to review, is that we have talked about how the conservation of momentum, that momentum is conserved, and that momentum is conserved basically because the change in momentum with respect to time equals zero. When the objects collide elastically, inelastically, completely inelastic, the momentum that changes based off that collision doesn't really change. It's the same with respect to the velocity of center of mass. So the change in momentum with respect to time is zero, especially when no external force is acting on the object. The net external force is zero. If they are acting on them, they cancel each other out. Well, angular momentum is L, and we're not quite sure why it's L. It's not something we can attribute to, but basically it's L. So if the conservation of momentum is true for linear objects with respect to time, well then it should be the same for rotating objects with respect to time. So the change in angular momentum with respect to time is zero when the net external torque is zero. So let's imagine for a moment that we have a stick, and that stick is nailed down to the table, and there's a ball approaching the stick on the flat table. So when the ball strikes the stick, and the stick being nailed down, the stick will then rotate about where it is nailed down, and it will rotate in that direction where the ball hits it, and it will begin to spin. The linear momentum here is not conserved because the object is nailed down, and that is an internal force causing the stick to not move linearly. Now, but when it begins to spin, the net external force or net external torque is zero, because when we look at this, torque is force perpendicular times radius, and the particular nail here in our stick is not acting perpendicular to the motion. So our net external torque is zero, so therefore our angular momentum is conserved. If we remember that momentum is P equals mv, but for angular quantities, what we use for mass is inertia, or moment of inertia, and what we use for velocity is angular velocity. So L equals I omega. And what we've learned from conservation of angular momentum is that the initial angular momentum equals the final angular momentum when a net external force is zero. Well, in this case, angular momentum initial equals angular momentum final when the net external torque is zero. So let's imagine we have a wheel with 5 spokes with radius r and mass m, and I equals 1/2 mr squared because those spokes will completely rotate through and it'll treat it like it's a disc. So we have our wheel. Our wheel is going to rotate about an axis, and because the spokes of the wheel have mass, the wheel will act as a disc, like a solid disc. So its moment of inertia will be 1/2 mr squared. And we're going to take a dart, and this dart is going to have a mass of m/2 and a velocity of v, and it's going to hit the edge of the wheel, and it's going to cause it to spin. Well, the wheel initially had no angular momentum. We had the moment of inertia being 1/2 mr squared, but it had no angular velocity, so L equals I times 0, which is 0. And the dart is like a point mass. We'll call it mr squared, where its radius is big R from the center. And its angular velocity is v over r. And that's one of those equations that we have when we were doing our angular velocity and angular acceleration from the last couple units. So what we have here is we have our velocity heading in one direction, and then our radius from our dart to the center of our circle being r. And that's the fixed point there. And what we're worried about is velocity perpendicular. The velocity parallel doesn't do anything for us. The reason we only care about v perpendicular is because velocity parallel does not cause the wheel to spin, or does not cause the dart to cause the wheel to spin about an axis. If the dart was to travel right down the radius r into the center of the wheel, it would just hit the center of the wheel, and it would be a linear momentum problem. What we are worried about is v perpendicular. V perpendicular causes things to rotate. So we have this velocity that it's traveling at, and it has both x and y components, if you want to think about it like that, but it basically has parallel and perpendicular motion to the axis, or to the wheel. So the only part of the velocity that our dart is traveling at that we care about is velocity perpendicular, so we can create some type of torque, some type of spin. So to determine v perpendicular, what we do is we use the angle theta and recognize that the v perpendicular is v sine theta, as if it's the side opposite the theta. So we use v sine theta, much like we did when we were doing projectiles. And so now we are worried about v perpendicular when our dart's heading toward our wheel. And so omega, we have to be very particular about what velocity affects our omega. V parallel does not affect our omega because it's more of a linear thing and just causes linear momentum. V perpendicular causes more of an angular rotation, and so omega is focused on v perpendicular. So we have v perpendicular for our dart coming in, and it equals v sine theta over r. So now we have our angular momentum is mr squared times v sine theta over r. Simplifying that equation, we can cancel out the r on the bottom and one of the squares, and we end up with mv open parentheses r sine theta and close the parentheses. Alright, so let's take a look at our wheel again. We have our v perpendicular, we have our velocity vector, and then we have our v parallel, and then we have our radius r. And when we look at this, our angle theta, we have that side, it creates that triangle. And opposite theta is the radius of our wheel, little r. And so little r will equal big R sine theta. Using our exact triangle here, using our triangle to find that opposite side, we do the sine of the angle times the hypotenuse to get little r. That allows us to write this equation as if it's mvr. Back this up a little bit. So if we were to look at this as if we moved to a point right here, see if I can, there we go, right here on our, right there in green. As my dart moves to that point, theta, the angle, will change. And so will the radius big R that the dart is from the center. But little r will not. It will still be related to big R sine theta. What that means to us is that the dart has a constant angular momentum as it's traveling toward the wheel. It's great to notice that the radius of the wheel does not change, and our triangle that we have with the dart changes based off its theta and its radius from the center of the wheel, but the radius of the wheel itself does not change. So it will always remain the same and have a constant angular momentum related to the angle theta and the big radius r. Now that we have the angular momentum for the dart, we can solve this problem. And what we have is the initial angular momentum is going to equal the final angular momentum, and what we're concerned about is how fast it is after the collision. So what we're really trying to find is how fast the wheel is spinning after the dart hits it at its edge. So we have m over 2 VR, and m over 2 was the mass of the dart, so we insert that m for the mass. We have velocity and r, and then that is going to equal I omega. before or after the collision. So m over 2 VR equals 1/2 mr squared plus m over 2r squared. I'm going to slow down for a minute and make sure we got all these things right. So the initial angular momentum of the dart, we have the mass of the dart, which we got from right here. Plug it in. It has a velocity, which we got from here. Plug it in. And then it's the radius, little r. And that little r is the radius of the wheel. And we found all this by doing all the angular momentum of the dart, all of that over here, and we ended up with this as our answer. And that's pretty much what we just plugged in. We just plugged in the mass of the dart in. And the initial angular momentum of the wheel was 0. It wasn't moving. So now we talk about how the angular momentum afterwards. So the angular momentum afterwards is equal to the moment of inertia of the system afterwards and the speed of that system angularly afterwards. The moment of inertia afterwards is the moment of inertia of the wheel, which is 1/2 mr squared we have from here. So we will plug that in. And then that will be added to by the moment of inertia of the dart spinning around the wheel, which is going to act like a point mass. So it should be mr squared, but the mass of the dart is m over 2, so we plugged that in, which again, m over 2, we got from there. Plug that in for the mass and treat it like a point mass because it's going to spin around the outside of the wheel. So it's mr squared, but it's mr squared over 2 just because the mass was over 2. So 1/2 mr squared plus 1/2 mr squared is going to end up being mr squared. So we'll let this run for a little bit. So we have m over 2 VR is going to equal mr squared times the angular velocity, and the m's and r's are going to cancel here to where we end up with, after we cancel and then we divide the r over, that the angular velocity equals v over 2r. And so that's how we have that it's the units for angular velocity. And really, once you have the initial and final angular momentum, all you have to do is find the new moment of inertia for the system, depending on your system, whether it's a wheel, disc, dart hitting a wheel that acts like a disc. You have to plug those in, and then you're good to go. Everything after that is being able to cancel out variables and get to finding your angular velocity, especially since what we were looking for was how fast the object was rotating. But before we move on, we're going to try to clarify this a little bit more. So now we're going to talk about finding the angular momentum of a particle moving with respect to an axis. So here we have a pivot point and a particle traveling at a line of action toward Let me run this back a little bit. It's going a little too fast, and make sure I'm really clear, because this is something that can be really confusing if we go too fast. So what we have here is a fixed axis, a fixed pivot point that we have to locate. An angular momentum is always taken about a fixed point for the entire system, so we have to make sure we locate it and label it. So this is our pivot point. Most of the time it's going to be where something is nailed down, or it also could be the center of mass of the entire system if it's something is not nailed down, and that's usually very easy to locate. So we're now going to have a mass m, and it's traveling with straight line velocity toward our object. And it's going to hit a point that we're going to call, or it's going to be traveling at a point we call line of action. And it's going to hit a point some distance A away from our pivot. And we're just going to call that distance A, and it should be something that's very easy to locate, or it's some distance A from the line of action. So you're looking for the distance between your pivot and your line of action. So we should have that L equals I omega. Now I'm going to try to explain my previous example a little bit better than I did previously. So we're going to have a mass spinning about a point. We're going to have a mass spinning about a point, and at any point we're going to have the radius be r. So that mass is spinning about that point in the center there, and it's going to have some velocity v. And that velocity is perpendicular to that radius. And the relationship we were talking about before when we said omega equals v over r, the definition of omega had to do with the specific velocity here being considered tangential. Tangential velocity. And tangential for a circle is considered to be perpendicular to the radius. And that is why we can say that that is the perpendicular velocity. Now if we look at our system over here, I have drawn our radius from our mass heading toward our system as at a line of action, and I've drawn the radius for our system, and that velocity is not perpendicular to our radius in our system. So what we have is a velocity that is considered to be parallel to our radius, and we call that our radial velocity. And the other part of our velocity is perpendicular. And that is velocity perpendicular that we are going to use for our omega. So using some simple trigonometry and using the angle theta here, our v perpendicular will equal v sine theta. So that means that our angular momentum will be mr squared, because that's a point mass heading toward our system, and our omega, which will be v perpendicular, which happens to be v sine theta, over r. We can then simplify this where our r's go away, and we have angular momentum equals m times v times r sine theta. And A is going to equal r sine theta. And we know that by looking at our system, that if we have this side being A and we have the angle theta, that A is going to equal r sine theta, opposite over the hypotenuse there, r sine theta. So now we can substitute in r sine theta, or A for r sine theta, and our angular momentum equals m times v times A, where A is the distance from the pivot point to the line of action. Now there's another way to do this, and the other way is to do R cross P, where this stands for a cross product. Now a cross product is a way to multiply vectors, and what it does is it deals with things that are perpendicular to each other. Another way to write this is RP sine theta. R cross P is RP sine theta. Now a cross product is at maximum when R and P are at right angles to each other. And so what this is saying is that the angular momentum is at a right angle to the radius and a right angle to the momentum. And the angular momentum is going to be the biggest when it's at 90 degrees. So it prefers them to be perpendicular. So moving on, what we get is that we get RMV sine theta, which is exactly what we have up here above. So either way we look at it, that the angular momentum is going to equal MVA, where A is the distance from the pivot point to the line of action. You can also do it with the cross product, but you're basically going to end up with the exact same equation where you're going to have mass times velocity, and then you're going to have r sine theta basically being perpendicular, sine of 90, some distance away from the pivot point. And we'll get more practice with this next class.